We spent some time in this module talking about how one might actually measure the enthalpy change associated with a chemical reaction using a calorimeter. In this particular video, though, we're going to talk about a really great method that uses tabulated data, and from it you can estimate the enthalpy change or calculate the enthalpy change for a wide variety of different chemical reactions without ever entering a lab at all. And so this is a tremendous utility for those of you who want to go on and learn something about the energy changes in reactions in a variety of different circumstances. So our learning goals are going to be to use a reaction sequence to find a change in enthalpy, and then to talk about defining standard states and how they can be used as a reference, and in particular how tabulated values of them can be used to determine enthalpy changes for reactions. So let's talk about some rules for combining the enthalpy changes for different reactions. Okay, enthalpy change for a net reaction, that is a reaction that is made up of several reaction steps, is simply going to be the sum of the enthalpy changes for all of the steps. So for example, if we have a reaction system that looks like this, and it's very abstract, but I think you can see that it's basically two reactions added together to get a net reaction, that the enthalpy change for the net reaction is just going to be the sum of the two. And this is very similar to what we did in another video where we talked about the same kind of thing for forming ethane from its elements. Now, if we have a reaction that we reverse its direction, the enthalpy change for the reverse of that reaction is going to be the negative of the enthalpy change for the forward reaction. So for example, if we took the first equation in the first example, a plus b going into c, and turned it around so that c is going to a plus b, we would find that the enthalpy change for that is now going to be the negative of delta H1. Now, this is pretty easy to see. If I have an endothermic reaction where I go up from the bottom line to the top line and it's got an enthalpy change of delta H1, the reverse reaction is going from the top line to the bottom line. So it's going to be the same distance in energy space and enthalpy space, but the opposite direction. So it'll be negative delta H1. The final rule is that if we have a reaction that say reaction 1, A plus B goes to C, and we multiply it by some number, the delta H for that multiplied reaction is just going to be the same multiple, but of delta H1. So for example, if we have little a times A plus little a times B going to little a times C, the overall enthalpy change will just be that same constant, little a, times the enthalpy change of delta H1. This is just a vestige of the fact that enthalpy is an extensive property, so when we magnify the amount that we're taking through a reaction, it's going to multiply the delta H. So these three things are basically, the sum of them together is Hess's law. Hess's law is about combining reactions together and the rules that would enable us to calculate the enthalpy change for that combination of reactions. So let's use it in a real example. Let's suppose that we're interested in studying the formation of ozone in the stratosphere, and that occurs by diatomic oxygen colliding with single atoms of oxygen to make ozone. And we want to know what the enthalpy change for this reaction might be. Now, this is a very difficult one to measure in principle in the lab because you also have oxygen atoms colliding with one another and forming diatomic oxygen. So you've got more than one reaction occurring in the vessel at a time, and it's very difficult to control it so that only one reaction is happening. So this is a reaction that we might be interested in, but we would need to find an indirect way to determine it. So what can we measure? Well, we can measure ultimately the enthalpy change from going from 3 O2s to 2 ozones, and we find that that delta H is 286 kilojoules per mole. We also can measure the energy needed to break apart an oxygen molecule to form two oxygen atoms. That's just the bond energy of the oxygen molecule, and that's 498 kilojoules per mole. So with these two pieces of information, we can actually organize this use Hess's law to determine what the enthalpy change for the ozone formation reaction, the first one listed on this page. So let's organize them so that the sum is the desired function, desired reaction. So now we look at the reaction that we want as O2 plus O going to O3. All right, so O3 appears only on the right-hand side of that equation. of the two reactions that we can measure, O3 only appears in one of them, and that's the first one, and it's on the right-hand side. So we're probably going to need that equation to be listed in its forward direction. And here's an example. We only have one O3 in the reaction of interest, so we're going to have to multiply through equation 1 by 1/2 in order to get one O3 on the right-hand side. That means we're going to have this sort of odd creature, 3/2 times an oxygen molecule going to one ozone molecule. In order to find the delta H for this, it would just be the 1/2 times the enthalpy change for the original reaction. So it's 1/2 of 286. So the enthalpy change for this 3/2 O2 going to 1 O3 is 143 kilojoules per mole. Now what about the other stuff? Well, the only place where oxygen atoms appears in the two equations that we can measure is on the product side of the second equation. We need it to be on the reactant side, so we're going to have to reverse that equation and basically consider, instead of the equation 2 as it's written, consider the equation 2O going to form O2 molecules, in which case delta H would be the negative of 498 or negative 498. Now, we also have only a single oxygen atom in our equation of interest, so we're going to have to multiply through that by 1/2. So that ends up giving us this as our trial equation. Negative 1/2 times equation 2 would give us one oxygen atom going to form 1/2 of an O2 molecule. I know it seems a little crazy, but bear with me here. Think of them as moles, perhaps. Then the delta H for that process is going to be negative 1/2 times the enthalpy change for reaction 2, which is 498, and when we multiply that out, it'll be negative 249. So now we've got things in place. If we add up these two equations, you'll notice that we have 3/2 O2 on the left side and 1/2 O2 on the right side. Well, we can always subtract 1/2 O2 from both sides of the equation without changing the value of the enthalpy change, and then we'll get the net reaction that we want. So if we draw our line across, add up these equations, eliminate things that are on both sides of the equation that are the same, we will end up with the reaction that we want. It is formed by taking 1/2 of the difference between equation 1 and equation 2, and the net enthalpy change is 143 minus 249, or a negative 106 kilojoules per mole. All right, so this gives you a sense of how we can get very useful information just using Hess's law and some tabulated information. Now let's expand a little bit on that last bit, on the tabulated information. Talk about reference states. A reference state is basically, for chemical substances, it's when the substances are in their most stable form at standard temperature and pressure. So we define this differently for different physical states. So for example, for gases at 1 atmosphere pressure and 273 Kelvin. For solids, it's the most stable structure at standard temperature and pressure. So for example, carbon, the most stable structure is actually graphite, not diamond. And believe it or not, if you had a piece of diamond and you waited around for millions of years, it would spontaneously, ultimately, convert itself to graphite. But I would say don't do the experiment because you'll be dead long before it happens. But solids choose the most stable form at STP. Solutions are their form when they're at 1 molar concentration. So now we're going to use these standard reference states for atoms, molecules, elements, and so forth to define standard enthalpy changes. So it's when we do a reaction and all of the species in the reaction are in their standard reference states, then what we have gotten from that is the standard enthalpy of the reaction. Now we can actually get this from another thing that is often tabulated, in fact what I would recommend, and that is something called standard enthalpy of formation, delta HF of 0. By the way, the little superscript 0 is telling you that it's in its standard reference state. The little subscript F is that it's a heat of formation, which has a very specific meaning. It is the delta H that one would get if one were to run a reaction that converted the elements that go into a compound into that compound with everything in its standard reference state. And we'll see some examples of that in just a moment. Now, what we've described here is basically sea level for molecules. This is the reference through which we're going to compare everything to evaluate enthalpy changes of reactions and so forth. So now let's see how we might do this using the heats of formation for things to get a reaction enthalpy. And to do this, we're going to consider the reaction of ethanol with oxygen to form acetic acid and water. Okay, so ethanol is CH3CH2OH, acetic acid is CH3COOH, and I think you recognize oxygen and water. Now what we would want to do is first go to a table of values, and there's one linked in the course in Blackboard, and find heats of formation for these different quantities. And if we did that, we would find that the heat of formation for ethanol is negative 278. This is all in kilojoules per mole. I'll skip oxygen for a second. The heat of formation for acetic acid is negative 484, and the heat of formation for water is negative 286. Now what about oxygen? It's given as a heat of formation of 0. Well, since oxygen is in its elemental state, basically the heat of formation measures its change from its element to its current form, and that's just O2 going to O2, so that it has to be 0 by definition. So what does all this mean? Okay, well, what is the reaction that involves a heat of reaction? Well, here it is for ethanol. We're going to take 2 carbons in their in most stable form at STP. That's graphite. So it's 2 atoms of graphite atoms. It's 3 molecules of hydrogen at 1 atmosphere pressure. And it's a half a mole of oxygen at 1 atmosphere pressure. And then it's going to create ethanol liquid. All right, so if we were able to do that experiment, to put those things together and have them mixed to make ethanol, the heat of formation that we would measure would be negative 278 kilojoules per mole. That's what the heat of formation is. So what we have on the left-hand side are elements in their standard reference states, and on the right-hand side it'll be the molecule that we're interested in its standard reference state. So it turns out that we can write any reaction enthalpy, any standard reaction enthalpy, in terms of these heats of formation as follows. The heat of reaction, the standard heat of reaction, is going to be the sum of the heats of formation for all the products minus the sum of the heats of formation for all the reactants. So it's basically the change that occurs from going from reactants to products. Now, another piece that I couldn't easily add to this equation is that you must multiply these heats of formation by the coefficient in the balanced chemical equation. So if there was a 2 in front of the molecule in the balanced chemical equation, you would have to multiply its heat of formation by 2 in calculating the standard reaction enthalpy. So let's see what this looks like when we go back to our problem now to find the reaction enthalpy for ethanol plus oxygen going to acetic acid and water. Well, we would multiply all of the heats of formation by their balanced equation coefficients, but they're all 1 in this case, so it really doesn't matter. Now, if I write out what this means, it's the heat of formation of acetic acid, CH3COOH, plus the heat of formation of water minus the heat of formation of ethanol. We obviously don't have to include oxygen because its heat of formation is 0, and this will generally be true in any reaction that has an elemental substance in it. You will not have to worry about its heat of formation. So when we plug in the values here, we'll get negative 484 minus 286 for the first 2 terms. The third term is negative 278, but we're subtracting it, so it'll end up being a positive 278. And the net result of all of this is a heat of reaction of negative 492 kilojoules per mole. So you can see simply by using tabulated values without having done a single thing with a calorimeter, we have actually found the heat of reaction for a fairly complicated reaction here just using the tabulated values. I hope this makes sense. If not, please give me a ring. Let me know that you need some help.